Can you hear me?
Yes.
Yes.
Perfect. So hello and welcome to today's webinar on facing high temperature concentrated solar power for energy applications. My name is Nuria Ferreira. I'm part of the team in charge of dissemination, exploitation, and communication activities within the Samsung project. And today I'm very happy to introduce these sessions, which is organized as part of the Samsung project and with our concentrated solar power sisterhood community. Today we will explore some of the major challenges and the innovative solutions that are being developed to overcome the barriers of the concentrated solar power technology. So let me share my screen. Okay. So here's a quick overview of what we will cover in these sessions. We will start with a brief introductions to the concentrated solar power and its importance in the energy sector. Then we will discuss the key challenges that arise when we are scaling the CSP system to the high temperatures. Following that, our partner project from the CSP sisterhood community represents their innovation, their contributions. And finally, we will open the floor for your questions in our question and answer sessions. So please write your questions or comments to whom the question is addressed in the question and answer sections. So let's start analyze what is CSP and what is important. As most of you already know, concentrated solar power is a renewable energy technology that generates electricity by concentrated sunlight to produce heat. And this heat is then used to drive a turbine or engine connected to a power generator. And why it's important, why the high temperature CSP technology is important. Unlike photovoltaics, the concentrated solar power has the advantage of integrating thermal energy storage systems, which make it able of providing electricity even when the sun isn't shining. By operating at high temperature, it's significant boost efficiency and enable advanced power cycles like supercritical CO2. Beyond electricity as well, the CSP also plays a crucial role in industrial applications, providing high temperature heat for process such as, for example, the hydrogen productions. And also it's important with thermal storage that the concentrated solar power ensures also the continuous and dispatchable clean energy. This means that we are able to replace the fossil fuels and also accelerate the decarbonizations. But what are the challenges in these high temperature CSP systems? First of all, the heat transfers and storage systems. Conventional technologies, such as, for example, the molten sands, have limitations when they are subjected to high temperatures. We need new solutions that are both reliable and also cost-effective. Second, the materials, components like receivers and thermal storage media mass withstands extreme temperatures while keep stability and also performance. And it is also implies that we need advanced materials with very good exceptional thermal and mechanical properties. First of all, the efficiencies. As we rise operating temperatures, keeping the efficiency in heat transport and conversion maybe becomes increasingly complex. And finally, the integrations. Since adapting the high temperature CSP systems to existing energy grids and industrial process also have its own barriers, its own challenges. So to overcome these challenges is why different innovative projects are born. In this workshop, we will present 6 projects that are part of the CSP Sisterhood community. Each of them will share their innovation, their unique approach and contributions to these fields. So they are starting to present, and please feel free to note down any question you have, as we will address them during the question and answer sessions. So we will start with the aesthetics KSR. Please, would you please share your screen?
Yes, I'm going to share my screen.
Perfect.
Okay, can you see something?
Yes.
Okay, perfect. I'm going to present the ASTERIX-CISA project. ASTERIX-CISA is the acronym for Air-Based Solar Thermal Electricity for Efficient Renewable Energy Integration and Compressed Air Energy Storage. And this project intends to combine compressed air energy storage with concentrated solar power in order to solve 2 key issues. On the one hand, we would like to provide energy storage for the power grid to be able to integrate more renewables. And on the other hand, we would like to make CSP more attractive because CSP is currently in a crisis because PV is much cheaper and CSP is currently too expensive. So we need a new business model to make CSP more attractive. And this we're going to try to solve in this project. We are 17 partners in 10 countries. The project will last 4 years. We are currently at the end of year 1 approximately, and we have about 7 million euros of budget, and at the end of the project we are going to be at TRL 6 to 7. And the concept is the following: during the day when PV output is very high, so we have very lot of solar energy available in the grid, we use this low value electricity to compress air and store the air in a pressure vessel or underground. At the same time, we heat air to a high temperature, to about 800 degrees Celsius, and we store that heat in a thermal energy storage system, which is usually a packed bed of rocks, for example, which is quite economical. And during discharging, so when the electricity prices are high, we are going to discharge the system and sell the electricity at high price. So in this period, we take the compressed air, we heat the air to high temperature using the heat stored previously, and the compressed hot air expands in a gas turbine, generates electricity, and we also try to recover as much heat as possible for additional electricity production, also for process heat supply or desalination purposes. So we'd like to optimize the system as much as possible to increase conversion efficiency. And the project develops certain key components for charging and discharging. For example, for charging, we have here a volumetric air receiver, which heats air to high temperature to about 800 degrees Celsius. Then we are developing optical sensors for solar flux monitoring, and also we are focusing on artificial intelligence-based heliostat tracking to improve the operation of the plant. And we're focusing on tailored compressor design for optimum charging operation. And during discharging, we need cost-effective air-to-air heat exchangers, because this is quite challenging because we have low heat transfer coefficient, so we need quite big equipment. So we need here special design to make this cost-effective. And we're focusing on turbine designs between 1 and 150 megawatt electric. This range is quite wide, so we have small-scale radial machines and large-scale axial machines here. And we're also focusing on integration of desalination to make best use of low-value heat. Let's have a look at the time scale We started in October 2023. We have been busy with thermodynamic optimization. We had a look at electricity prices. Then we're currently testing small-scale solar absorbers in a solar furnace in CMAT PSA in the south of Spain. And we also have been busy with artificial intelligence-based tracking control, for example. And towards project end, we are focusing on use cases. We're going to optimize the concept for different locations around the world. And we also will demonstrate the system, the concept, the small-scale prototype close to Almeria in the south of Spain. And here you can see already the 3D of the prototype, where we have a solar receiver, we have an air heat exchanger, and a small-scale hot air turbine, a small-scale expander, where we will demonstrate the KS combination with CSP at small scale. And that's it, basically. Thank you for your attention.
Thanks so much, Fritz, for your full presentation. The question and answer will be addressed at the end of all the presentation. So now it's the turn of the Array CSP future. So please, Christoph, if you are able to share your screen, would be great.
Let me try and see if it works.
Okay.
Just a moment. Sorry. Can you let me know if you see my screen?
Not for the moment.
Is something loading or not?
No, for the moment, not.
Nothing. There. Now?
Yes, now.
Okay, and let me go to presenter mode.
Perfect, great.
Okay. So I will present the project called the Bright CSP Future, which has to do with, let's say, integration of future potential CSP plants for Brayton cycles. A brief, let's say, overview of the project. This involves 10 partners. We coordinate it as DLR. It involves research institutes, universities, SME companies, and large industries that are, let's say, from 5 different countries. It will last 4 years. As I will show you later, we are just after the middle of it. And it's a proposal that was submitted, let's say, 3 years ago for a total cost of total budget of almost 3 million euros. They are partners from Spain, Germany, Denmark, Netherlands, and Greece. Now, what is the problem that we try to address? As it was already mentioned, the idea is that current state-of-the-art, let's say, CSP plants are inherently limited by low efficiency by using a steam cycle. So one idea is for them to become competitive is to be able to use, let's say, combined gas turbine Brayton cycle with a Rankine cycle, which will go to higher efficiency. And this will give CSP a competitive edge because these efficiencies cannot be reached with either PV or CSP plants operating with molten salts or oils that are limited to lower temperatures. So even though for the recent, let's say, supercritical CO2 Brayton cycles, we need to have a receiver which has temperature output at the order of 700 degrees. This excludes oils and molten salts. So now, again, taking into account that all these plants have to have storage, now we are left with only few heat transfer media like ceramic solid particles or rocks or air for that matter. And here we're going to deal with air-operated solar tower plants that can heat, just like you listened to that before in the previous projects, that can reach this kind of temperatures which are within the range, let's say, of the Brayton cycles. Now, The idea is that taken from industrial heat recuperation systems, where these regenerative systems for sensible heat storage consist of fire bricks, essentially bricks, and when the hot combustion gases from furnaces flow through them to make them hot, and let's say then cold air is charged through the already hot bricks, it gets heated and it's driven back, let's say, to the industrial processes. A similar concept is used for air-operated solar power plants like in Jülich that we have here. The receiver heats air. A part of this air is diverted to the heat storage, to the hot storage module, which is essentially contains ceramic honeycombs, essentially bricks that get heated. The other part goes to produce electricity during the day, and at night, cold air goes through the storage, becomes hotter from the hot bricks, and goes back to the turbine to produce electricity. A similar concept is used now. Only the storage system and this electricity, if we take away the CSP part, one can use the same thing to convert renewable electricity to heat to power, for instance, from photovoltaics or wind energy, with the excess electricity to heat air, which this hot air will be driven to the storage to provide, let's say, power when the renewable energy on the left from photovoltaics or wind is not available. So the same principle of, let's say, storage can be used not only for CSP, but for power generation. The limitation is obviously that one is limited by the receiver. So heat transfer fluids in principle cannot be heated higher than the temperature of the receiver. So in other words, let's say where one wants to use a combined Brayton cycle, this temperature has to be increased. And this is, if you add to this temperature, let's say, the enthalpy of an exothermic chemical reaction, and that's exactly what happens when you have traditional fossil fuel burners that they burn, let's say, gas and power the gas turbines. This thermal boosting, of course, the idea in this project is, instead of using fossil fuels, is to use an exothermic reaction of clean fuels of reduced redox oxides. Okay, so the idea is that during the day, with the heat coming from the solar plant, one can reduce a redox oxide from its oxidized state to the reduced one by releasing oxygen in the atmosphere. This is an endothermic reaction. And at night, when the sun is not available, one can pass, let's say, air through the reduced oxide, cold air to induce, let's say, this exothermic combustion reaction, regenerate the heat that was spent, let's say, to reduce the oxide, and get the heat back, reform the oxidized state, and do this in a cyclic process. So the idea is to make these sensible bricks that we showed before, not of inert material, but from a redox oxide, so we can generate extra heat in the same volume and do, let's say, hybridization of sensible with thermochemical storage. Furthermore, not only that, if we perform the oxidation with pressurized air instead of atmospheric air that was used for the reduction, we can shift the oxidation reaction equilibrium to higher temperatures. So the amount of heat we're going to get from the exothermic oxidation, it would be higher than that what we spent, let's say, to reduce the oxide. And this is how we can hope to achieve thermal boosting, so to achieve an airstream of higher temperature than before. Of course, this is at the expense of pressurizing the air. So the same thing, the same principle to design a heat exchanger regeneration thermal booster made of reactive redox oxide porous ceramics. We want to transfer heat from a non-pressurized airstream to a pressurized one and increase the temperature of the pressurized system. And this is how the concept would operate. From a receiver, we need to use a dual bed reactor system so that the oxide is reduced, whereas the other is oxidized. So the idea is that hot air reduces the oxidized oxide, let's say, to the far right. And in the other bed, the oxide is already reduced, so cold air is introduced, gets heated from the reduced oxide at the high temperatures to be driven, let's say, always hot air to the gas turbine. This is, and this is the second step. when the reactions are complete, we just switch the feed. So let's say the hot air reduces now the oxide in the other bed, and the cold air gets heated from the already reduced oxide, and always we have a stream of high temperature pressurized gas going to the turbine. So that's the concept. The material aspects now, okay, this is interesting, but what are the materials that we can do it? There are several materials that have been tested, like cobalt oxide, manganese, and so on. The first of them have different disadvantages like cost, toxicity, low reaction enthalpy, and so on. So now we concluded that we're going to deal with perovskite materials, that they are made of low-cost, non-toxic, earth-abundant elements, and they operate in a quasi-continuous way. Calcium manganite is the most, let's say, studied family for this class of materials. And of course, one can play with the composition to improve several characteristics. The operating temperature range is between 750 and 1100 degrees when reduction and oxidation takes place. This shows broadly how the project is structured, starts from, let's say, more basic steps to the integrated ones. We want to make, let's say, powders, then porous structures, then a dual bed, as we showed before, which will be coupled to a solar simulator facility, together with techno-economic and socioeconomic analysis. And as I said, we are just crossed the middle of the project. This shows briefly the various testing rigs and different porous ceramics that we have made out of perovskites, honeycombs, foams, small dimensions, larger dimensions, tested in furnace rings for the time being, mechanical properties testing. And just to conclude, I will just mention the results so far. That so far we were able to synthesize porous structure ceramics made 100% out of perovskites. These are robust enough, and we can use them later on for mechanical testing, whatever, and any other of tests. So they are, let's say, they have good mechanical properties. We believe that this is the first time that such a systematic protection of such structures has been reported. And also the idea is, the basic thing is that we demonstrated the proof of concept with this material. So the idea is that when you pass a cold air stream through, let's say, a reduced structure of this kind, the air should become hotter. So experiments in the test rings that I shown before have indeed shown that after we reduce the material, if we pass cold air through this kind of honeycombs, the solid itself can become hotter by 200 degrees due to the exothermic reaction, whereas the air stream that comes out of it becomes, let's say, from 75 to 140 degrees hotter, which is very good. And this is, I guess, as I say, also the first time that we demonstrated this kind of redox behavior as a sensible and measurable temperature rise of the heat transfer fluid. And we have also very high energy density values, much higher than the state of the art of the molten salts. And this concludes the talk. We still, of course, have a lot of work to scale up this stuff. So thank you very much for your attention.
Thanks very much, Christos. It was a very detailed and interesting presentation. And for sure, we will discuss it at the end of the webinar through the question and answer section. So then it's the turn of the Samsung project. Esther, could you please share your screen?
Yes. Do you see my screen?
Yes.
Perfect. I will put it in presentation mode. Okay, so I'm going to talk about Samsung project. And as you probably know, in the last year, there has been a significant increase in the power installed from renewable energies like solar and wind. But still today, most of the energy that we consume is not coming from these systems. And the problem is just that the generation is intermittent. So basically is that we cannot generate when we want. One clear solution to mitigate this problem consists, it's okay? consists on using stored energy systems. But if in the future we want a high penetration of renewable energies in our grid, like 60%, 80% or something like this, then these systems will need to store energy for long periods. Or what is the same, they need to provide a low storage capital cost. So among all the technologies that are compatible with these characteristics, thermal energy storage systems are one of the most promising ones. And the Samsung project, the aim of Samsung project is to develop this kind of system, in particular a solar to heat to power storage system. So the idea is that, first of all, we can convert the solar energy into heat by concentrating the sunlight using CSP optics. And then this energy can be used to heat up a phase change material. So this energy can be stored as latent heat. And the idea is that if the PCM achieve very high temperatures, which means to be above 1000 degrees Celsius, then this PCM become incandescent and it can be used to illuminate photovoltaic cells. And these devices can convert this radiated heat into electricity just by using low bandgap semiconductors that are suitable for the spectrum illumination of incandescent bodies, which is why these photovoltaic cells are called thermophotovoltaics. So regarding the solar to heat conversion part, the idea is to use a solar furnace, which is located in the Plataforma Solar de Almería. So the idea is that the sunlight comes from this aperture and achieve this first mirror, which is a parabolic mirror. And this mirror focuses the light in a secondary mirror that has a butterfly shape, as you can see here. This is more in detail. And the idea why we do this is because by using this butterfly mirror, we can split the total irradiance into 4 different spots. Because according to our simulations, the irradiance level achieved in every spot should be high enough to achieve the temperatures that we target. So the shape and the size of this spot will fit the shape and the size of cylindrical absorbers. The cylindrical absorber is this black part here. And surrounding the 4 cylindrical absorbers, we will place the crucibles that contain the PCM. So here you can see 4 crucibles. Here in this slide, you can see what is the specific shape of the crucibles that will contain the PCM. And as I mentioned before, this PCM is the element that stores the energy. In this project, we have studied different alloys, first of all, theoretically using simulations to predict which ones can be the more promising ones as PCM. And afterwards, we have fabricated and tested some of them to check what is the empirical value of the main parameters, like, for example, what is the energy density that can be stored, what is the melting temperature, and what is also the conductivity of the PCM. It's important to have a high conductivity in order to transfer the heat effectively. Regarding the heat to power conversion part, we have used 2 kinds of TPV cells, what it's called thin film TPV cells that include back reflector in the rear side of the cell to boost the efficiency up to 25%. And also what it's called metal grab-through TPV cells, where the front contact of the devices can be transferred to the rear side in order to increase the active area at module level, because this way we can remove some specific parts that are dedicated for interconnection of the devices. The idea of the project is to implement a demonstrator where all the parts that I have mentioned before are assembly, including also protective elements to avoid condensation in the TPV cells and also in the optics. And the idea here, for example, you can see the design of this unit and what is the basic principle. And the idea is that this design was also designed to be compatible with a scale up of the technology in the future. Because in the future, for example, if we want to increase the power install, we just need to replicate this unit several times. what we want to do is, once the demonstrator is implemented, we want to test different operational modes, like, for example, when the battery can be charged and discharged at the same moment, so storing heat and also producing electricity at the same time, or only storing heat, or only generating electricity, or just being standby mode. And we can change this from one mode to another mode just by moving some parts of the prototype, like the location of the PCM or the location of the TPV generator. And this is all from my side.
Thanks very much, Esther. It's really interesting how the project is already progressing, and all the development that you have already done, all the team of the Samsung project. So let's go to the presentation of P-Solo. So Marco, if you're able to share your screen. Thank you.
Yes. Okay. Okay, can you see my screen?
Yes.
Thank you. Good morning to all the audience. Today we'll present a brief introduction and status of the P-Solo project. I am Marco Binotti and I'm coordinating the project from Politecnico di Milano. So very briefly, we'll go through this outline, starting with a few, let's say, summary information about the P-Solo project. So the project itself, the acronym stands for Pyrolysis of Biomass by Concentrated Solar Power. And the idea and the scope of the project is to integrate together concentrating solar power and pyrolysis of biomass for the production of bioproducts such as bio-oil, pyrogas, and biochar. The project has a budget of about 5 million euros. I guess you see my pointer. It's a 4-year project coordinated by Politecnico di Milano, and it involves 9 partners from 4 European countries. Okay. What I wanted to say is let's move to this next slide, in which I will just give you a couple of information about, I wanted to say that we are almost at 1/3 of the project because it started in July 2023. But before, let's say, speaking about the concept of the project, just a couple of information for the ones of you which are not familiar with biomass pyrolysis. So the pyrolysis of biomass is a thermal degradation which occurs supplying heat in an inert environment. This heat should be supplied around 250-700 degrees C, so with no air. And basically, the thermal degradation will produce bio-oil, pyrogas, and char. What happens is, like it's reported in this schematic, is that usually the biomass is dried, then you have the pyrolysis reaction, and basically what you have is that the heat for, let's say, supporting the pyrolysis reaction, which is endothermic, is provided by the combustion of a fraction of the products. So typically the char and maybe a fraction of gases is used to heat up the pyrolysis reactor. And this is a loss of carbon, which is emitted as CO2. So it's a reduction in what we call carbon efficiency and in the overall yield of bioproducts. So the basic concept of the P-Solo project is to provide instead the heat for the pyrolysis via concentrating solar power. In order to, let's say, move the heat from the receiver to the pyrolyzer, what we use is a particle heat carrier. This is, let's say, a common use in the pyrolysis reactors. So typically, for example, it's used sand. So the idea is to use the very same sand as a heat carrier in the solar receiver. Of course, coupling the pyrolysis reactor with CSP allows also for a storage system to be integrated in order to increase the number of operational hours of the system. The other two features that moves to what you described at the beginning, so looking at the flexible energy market, are two features in which basically the system can absorb electricity from the grid when there is low-cost electricity, using an electric heating system to, let's say, in parallel with the particle receiver, to heat up cold particles with an electric resistance. Or better, with an induction heating system in our case. The other option is when electricity prices are high, there is the possibility to use the gas of pyrolysis to produce electricity, for example, via an internal combustion engine. What will happen within this project is that we will test different type of particles, of particulate carriers. We will test 4 of them in the pyrolysis reactors, and then 1 or 2 of them in the solar part. We will study, let's say, a standalone plant, but we will also evaluate the integration of this type of system with the biorefinery plant. About the experimental activity, basically we will test the system at TRL4. It is true that the single components may have even a slightly higher TRL, but the integrated system not. So we will try to test the system and the integrated system. The system will not be integrated, but the integrated concept and thus the optimization of the single parts for the overall operation at TRL4. So we will test 2 pyrolyzers, a rotary kiln receiver, the particle charge carrier, and the electric heating. So the receiver system will be a rotary kiln receiver tested DLR. It will have a power in the order of 15 kilowatt, and it will allow to use directly particles within it. While for the pyrolysis, we will have 2 different types of reactor. One is an Auger reactor, so a screw reactor, and the other one is the fluidized bed reactor. And then, as I said, the induction heating system and the particle charge separator will also be tested. The particle charge separator is an important component. As we are not burning char, we need to separate it to, for example, sell it or use it for other purposes. So very briefly, what has been done up to now? As I said, we are more or less at 1/3 of the project. So what was done at DLR was a characterization from the optical, mechanical, and thermal point of view of different particulate carriers. In particular, we tested 5 of them, plus biochar. And basically DLR found out and described all the relevant properties that will be required for the design of the receiver, and will also be valuable for the pyrolysis part. About the 2 pyrolysis units, what happened in this first third of the project is that we have adapted the existing units at CSIC in Spain, which is a fluidized bed reactor with a biomass flow rate of about 3 kg per hour biomass, and the Auger reactor available at a Record facility in Italy. Both systems will operate with 3 kg per hour with the different temperature range. Moving to the other, let's say, preliminary results and activity we are doing. Of course, the hardware is supported also by simulation activity. In particular, it is crucial to have a sustainable use of biomass. Thus, we decided to focus on 3 European countries, which are representing 3 sunny locations in the south of Europe: Italy, Greece, and Spain. And for these 3 countries, CTFC which is one of the partners of the project, is looking at, let's say, biomass distribution to understand which type of biomass needs to be selected. Of course, we decided to test just one biomass for homogeneity between all the plants, and this biomass will be pine wood, but we will, let's say, evaluate the potentiality of other biomasses for the scale-up study. Another important aspect as I said, is the separation of the particulate carrier and the char. So the design of the separator, which will be a fluidized bed separator, has been performed by Record together with Politecnico di Torino. From the modeling point of view, moving to the components, we know that pyrolysis is a quite complex, let's say, set of reactions. For this reason, we have a set of fluidodynamics or better say pyrolysis models, which combine together information at molecular and at reactor scale and describe the biomass as a set of simplified components and describe the reactor as a set of, let's say, simplified reactors to catch the fluidodynamics inside the reactor itself. This activity of let's say, micro and reactor scale simulation is performed at the chemical department of Politecnico di Milano. From the system point of view, what we have started is to trying to investigate and to understand the operation and the behavior of the rotary kiln receiver. So let's say the relationship between the type of motion, the flow regime inside the receiver and its design parameter, for example, the tilt of the receiver, the rotational speed, and so on. This, of course, implies a set of constraints on the geometry and thus implies impact on the optical and thermal efficiency of the solar tower, which will be coupled to this system. Finally, in terms of system simulation, we already have defined a system model in which we have the integration of the pyrolysis plant and of the CSP plant, but we haven't integrated completely yet the pyrolysis model, so this will be done in the coming months. We have defined a set of, let's say, key performance indicator. One of the most important is, of course, the minimum fuel selling price, which tells us what is the cost of oil produced. And here you can see a set of preliminary results of the conventional plant, so standard pyrolysis, of the solar plant, and of the hybrid plant, which is somehow a combination of the options. So the solar plant will have a limited number of operating hours. The idea of the hybrid one is to operate in some condition when it is possible, and when it is not, to use part of the char to sustain the reaction line in the conventional one, like in the conventional one. It is relevant to see that the emission to oil ratio is negative for the solar and hybrid case, meaning that we are somehow considering, of course, the carbon in the biomass as neutral, we are developing a potentially carbon negative system. And yes, this is the team of all the partners, and thank you for your attention.
Thanks so much, Marco. It's indeed a very interesting project. With a really interesting application using the concentrated solar power. So let's go to the Blastec project with Daniele.
Yeah. Okay, I'm going to share the screen.
Thanks.
Okay. Okay, can you see the screen?
Yes.
Okay, I'm Daniele Trucchi from National Research Council of Italy. I'm the coordinator of the Blastec project, which means breakthroughs in thermal batteries through zero emission, high temperature, static thermal to electric converters. The project started in July 2024 with a duration of 42 months. And by replying to a call in which the solid state conversion mechanisms were have to be tackled. 3 of them were previously tackled by partners of the Blastec consortium, thermoelectric thermophotovoltaic.
Daniel, we can hear you very well.
Twin temperature from 12 to 1600 degrees centigrade. So our focus is mainly on the solid state conversion technologies. We have three legs: thermoelectrics, fermionics, and thermophotovoltaics. The first aim of the project, I told you it started 6 months ago, and so we are working on the single stages to increase their efficiency. This is the first aim, by maximizing efficiency and output power in this range, apart from thermoelectrics that will work at lower temperatures between 800 and 1000 degrees centigrade, because it will be hybridized within with the other ones. In which way? We will prepare two hybridization conversion systems, one made with hybridization of fermionics and thermoelectric generators, and the other ones based on fermionic and thermophotovoltaic generators with their own efficiency and their own output power density. And to demonstrate them within two demonstrators, one based for solar to heat to electricity, in a thermal battery for sensible heat, and the other one, latent heat thermal batteries for electricity to heat to electricity demonstration. So let's talk more in detail about these two concepts. The first concept is based on fermionic thermoelectric generators. It was patented by National Research Council, so the partner which is coordinating the project. There are two stages. One stage is fermionic energy converter, thermal in series with the thermoelectric generator, and we would like in BlazeTech to build an absorbent and storage system which is fed by concentrated solar radiation, where in the process facilities which is in the Cyprus Institute in Pentacomo, and this system, this solar tower system is inaugurated in 2015 in Cyprus, and it is going to be updated up to 70 tilt-roll heliostats of 5 square meters each. So we will test the solar to electricity, solar to heat to electricity system there. And how to do this? We are developing new materials, and we are applying materials which are resistant to and stable to high temperature. So refractory metals such as molybdenum as an absorber, lanthanum hexaboride as an emitter, and other materials which, anyway, if they are exotic, they are developed by CNR in very, very ultra thin on substrates, and we will integrate the Thermagy technology by RGS Development, which is a company involved in the project, and in which the capability of a operating temperature up to 900 degrees centigrade and a high conversion efficiency. We will integrate and adapt these systems within the converter. The other system is based on fermionic thermophotovoltaic system for a latent heat thermal battery, in which the concept was patented by Universidad Politécnica de Madrid, which is based on similar materials to the thermoelectric on the fermionic part, but it has got a core with a multi-junction thermophotovoltaic cell based on indium gallium arsenide thermophotovoltaic cell that will be developed by Universidad Politécnica de Madrid. The system will be tested at lab level in high temperature electric furnace at the Universidad Politécnica de Madrid. There are still open changes within the project, and we will try to tackle them. For example, the electric microspacer, we need that the two electrodes of fermionic energy converter should work a micrometer distance. So the Swiss partner of BlazeTech, CSEM, will work to solve this issue by developing dielectric microspacer, resistant and thermally resilient also. And also, IonVac Process, an Italian company, will work on encapsulation technology because we want that this system work under vacuum. So we are developing single stages based on thermoelectric generator, thermophotovoltaic stages, which they are all solid state systems. It means that they are steady state, so with minimized maintenance, long lifetime, high efficiency if working at high temperature, and scalability in a small system and in large system. Systems based on hybridization of fermionic thermoelectric generator and fermionic thermophotovoltaic generator to combine the advantages of both the systems. And we are developing two thermal battery demonstrators, one for sensible heat based on fermionic thermoelectric generator fed by concentrated sunlight, and the other one based on latent heat and on a mechanism based on fermionic thermophotovoltaic fed by an electric furnace. Thank you for the attention.
Thanks so much for the presentation. Then we will finish with the cooperant projects. Patricia, if you have the possibility to share your screen.
Okay, thank you, Nuria. I will start the presentation, so you should be watching the screen pretty soon, I hope.
Yeah.
Okay, perfect. So good morning to everyone. Thank you for the audience joining the event today. I'm here to present a cooperant project, which is a research and innovation action that started just 4 months ago. And we aim to find leading-edge cooperative advances towards the next generation of the CSP technology. So the situation nowadays, it's pretty promising for renewable electricity and renewable energies in general, but if we put the focus on CSP technologies, we can see that despite all the efforts, we are a bit far off achieving the goals that we have set from the different agendas at European and international level. This could mean that we need to have more or less install a CSP capacity of almost 1 terawatt. This could mean that we need to grow around 6.7 gigawatts each year. And right now in Europe, we are 3 times less than this. So it's clear that the rate is not the proper one. We are not on track of the climate energy agendas. And in order to fulfill the European net zero scenario emission target by 2050, we would need really some disruptive innovation in this specific technology to reach these goals. And this is exactly the aim. Our motivation to create this project is trying to find out solutions for the limitation of CSP and thermal energy storage. We have been discussing them today along the different partners' presentation, but again, a focus on the higher cycle efficiencies that are needed in order to run more efficient operation cycles, such as the supercritical steam ranking, supercritical CO2 Brighton cycles. We have been working on them during the presentation today. Related to the thermal energy storage, they are limited to a temperature nearly 600 degrees Celsius that prevent us from reaching these high temperatures that are needed for the cycles that we mentioned before. Also, the reduction of costs is important. Working at very high temperature will bring us to develop advanced material and critical components that need to withstand very harsh conditions, and this is usually not very cheap. We need also some digital tools accompanying to all the technological developments in order to support the integration and manage the operation of these cycles. And the industry is still reluctant. This means that there is very scarce proof of demonstration novel CSP approaches and novel prototypes that really convince the industry to bet on these new advances. And finally, there is a general lack of consideration of human health and sustainability impacts. So this is everything that we would like to tackle down within the Cooperant project, and I will proceed to present now the concept and the main innovations that we have for that. We will be developing very innovative solution, starting at TRL 2 and 3, up to a validation at prototype level, aiming for a revolutionary technological integration to unlock this third CSP generation that should come. How? First of all, reaching high temperature operation at approximately 1000 degrees Celsius for coupling these efficient power cycles, overcoming the variability of novel thermal energy storage to improve the dispatchability of the intermittency of solar energies, and finally upscaling feasibility in line with the CSP roadmap, supported by the digitalization. In Cooperant, I will be presenting the three different solutions. The first one is at technological level, the development of a prototype that integrates very new advances at different points of the cycle. So, for example, we have novelties in terms of a high-performance open volumetric receiver to increase the solar absorption and provide this heat to a cycle operating with air as heat transfer fluid. If we focus now on the thermal energy storage, we are proposing a hybrid packbed system combining both sensible and latent heat. And at material level, the development of high-temperature ceramic solid-state mixture for the sensible part and phase change material based on molten salts and new metallic PCM that will provide us the chance to operate at this high temperature without degrading. The second solution is an artificial intelligence tool that will be monitoring and control the management of both the thermal energy storage and the CSP generation. It consists of two different modules, one oriented to a distributed control with reinforced deep learning techniques to develop a digital twin of the cycle, and a second one that would be helping the decision support in terms of feasibility and replicability with multi-criteria design optimization algorithms. And the third solution is the Cooperant Transfer Package, that this is a kind of program that involves a multi-sector industrial board, a lot of activities of clustering, networking, and synergetic actions, and it will provide a participation in the different dissemination, exploration, communication activities, training material, open publication, the live lab demo, and this will boost the impact at scientific, industrial, policy, and social acceptance level. I would like also to take the chance to present the consortium. It is a very interdisciplinary team with a total of 7 different partners from 5 different countries. This is a European project funded by the Horizon Europe, but also with contribution for the Swiss government with the SERI. And we have either as coordinators of the project and also developing the digitalization tools, craft block with the hybrid design for the thermal energy storage and the manufacturing CMAT for the demonstration testing of the CSP, OLOS to evaluate all the environmental, socioeconomic, gender, and ethics issues, PCM product developing the PCMs for the latent heat storage part, the University of Lucerne supporting all the thermal energy storage design, characterization of the different formulation, and NGSER to focus on the study of the open volumetric receiver for the solar concentrator part. Along with all the consortium team members, we are working very closely with the industry from the very beginning, from this early state of the project. We have a stakeholder replicability board that offers a unique opportunity to overcome these obstacles, acquiring knowledge and evidence from the project itself and being in touch with the consortium and focusing on potential applications. In this panel, we have Lonza, one of the biggest European pharmaceutical industries. We have the Energy Intensive Industrial Partnerships, ASPIRE. We have an energy agency in Italy, FMI, that it has already CSP integrated with district heating, and they are interested in exploring also options in terms of thermal energy storage, and all the CSP network bring by CMAT. Of course, this is open to new members in case any industry is interested, and this will provide an opportunity to identify potential applications, to provide specification of these processes that needs to be assessed. We will be giving the best practices, recommendation, anything that we find out during the execution of this project. Being able to validate and even test these promising solutions at technology and the tool level, and also give feedback to the open reports that we are developing, participate in training, dissemination, communication action, and also in stakeholder events as the one we are present today. So I will also would like to say that in case you are interested in join us, you can contact us by means of email, LinkedIn, or even the website. So thank you very much for the time.
Thanks very much, Patricia, and thanks very much to all the speakers for your contributions. We don't have so much time, but maybe we can spend 5 minutes answering the questions that are included in the question and answer sections. If we go to the questions, we have to, I can move the up here. Okay, one of the question is already answered by Fleets, which is can you explain what benefits you get from this configuration where a CSP system supplements the heat in a compressed air system, and how does it compare to having the two systems separate? It was answered, but if we could share with the rest a very brief explanation, just a very brief explanation.
The main benefit is that we have the carrier system CO2 neutral, so we don't need natural gas for heating the air before expansion, so we use the heat of the CSP system. And on the other hand, the CSP plant is more efficient than the standalone one, so that's the two main advantages.
Okay, thank you.
Yeah.
Another question for you. Yes.
Yeah, that was the question about the pressure we use for the small scale artificial storage vessels. We propose up to 150 bar storage pressure, and for the large scale solution underground, we are working at 80 bar pressure.
Okay, thank you, Felix. And the last question is for Pisolo. Which software did you use to make the process flow diagram, Marco?
Okay, so I don't know if the question is about the graphic aspects, which were made, I think, with the Visio and PowerPoint. While I can add that process flow diagram and the calculations were made with Aspen Plus software in terms of calculation, and the solar part is handled outside with the Solar Pilot for the design of the solar field, while we have in-house codes for the determination of the receiver efficiency. In some of the publication we made, we used our own codes for falling particle receivers, which are not the ones that will be included in the PyZor project, while we have a task for the development of the rotary kiln model that will be developed during the project.
Okay, great. I think that there is not more questions. So basically, to sum up, from my point of view, the high temperature CSP system hold immense potential for addressing the world's energy needs, but they also present complex barriers, complex challenges. And I think that this kind of collaborative efforts by dissemination results and also cooperating together, that we are making significant progress in overcoming these barriers. And from my side, this is all. I will send you all the presentations, and also we will upload the video in the YouTube channels. I'll set also due to the link. So thanks very much for your interest in participating in this workshop. Thank you very much. Bye.
Thanks to you.
Bye. Thank you for
Thank
organizing.
you.
Thank you for
Thank you.
organizing.
Bye.
Thanks,
Bye,
everybody.
bye, bye.
Bye-bye.
Bye.